All right, now we introduce the concept of independent domination number. So I of G is defined to be the size of the smallest independent dominating set. So you want it to be both dominating and independent. So for our graphs we have last time, the independent domination number of the clique and the cycle graph are the same as the domination number because we gave examples of dominating sets that also happen to be independent. And as we'll see in a little bit, the domination number is actually a lower bound for the independence number, and so we actually have equality here. On the other hand, for our tree, the domination number gives us a lower bound of 2, but if we want to be independent as well, we can't find an independent domination set of size 2. The smallest we can get is 3. So that tells us the independence domination number of this tree is 3. So first we discuss lower and upper bounds for the independent domination number. A lower bound is given by the domination number and an upper bound is given by the independence number. And this sort of makes sense because if we let I be a minimum independent dominating set, then it has the same size as the independent domination number. But since it's not guaranteed to be the smallest dominating set, there might be a smaller dominating set. Therefore, you have this upper bound. On the other hand, since it is an independent set, it might not be the largest. Therefore, it is bounded from above by alpha of G. So what we're going to focus on for the rest of the lecture is looking at a case when these two numbers are the same. As we saw, they're the same for cycles and complete graphs. We want to see when else that happens. So the theorem we're going to be interested in is about claw-free graphs. So claw-free graphs pop up a lot in graph theory. They haven't popped up yet in this course, but here they are. We say a graph is claw-free if it doesn't contain a claw. Induced claw. So a claw is K13, so it looks like this. And we say it's claw-free when you don't have an induced claw, which means whenever you have a claw, you must have one of these other edges. And so some examples include the complete graph, the cycle, and line graphs of a graph turn out to also be claw-free. So the theorem is that if G is claw-free, then the domination number is equal to the independent domination number. So we already know the inequality one direction, so we have to show it the other. So what we need to show is that for any minimum dominating set, so something of this size, there exists an independent dominating set of the same size. So then that would force the equality. So suppose that D is a minimum dominating set. We're going to build up our independent dominating set in two stages. First, we're going to take a maximal independent set of D. Then what we're going to do is we're going to delete D and delete the neighborhood of every vertex in I1 and call the remaining set X. And we're going to let I2 be a maximal independent set of X. Then we're going to let I equal I1 union I2. And so our claim is going to be that this is an independent dominating set of the same size as D. So first we need to show that I is independent. Take two vertices in I, and suppose there's an edge between them. Since I1 and I2 were independent by definition, it must be the case that one of these vertices is in one and V is in the other. So without loss of generality, we assume U is in I1 and V is in I2. Well, then V is in the neighborhood of U. But since I2 is the subset of X, and X consisted of deleting D and all the vertex neighborhoods of I1, we have a problem. Because this implies V is not in X, despite being in I2, which is contained in X. So we have a contradiction. Therefore, the edge couldn't exist, and I is in fact independent. Next, we need to show that I is dominating. So for every vertex in I, it's in I. So let's take a vertex that's not in I. Suppose that vertex is in D. Since I1 is a maximal independent set, we see that adding X to I1 can't be independent, which means there's an edge. It can't be contained in I1, so it has to have X as one of its endpoints. Therefore, there's a vertex in I1 adjacent to X. And thus, X is dominated. Case 2, X is the neighbor of some vertex in I1. Well, then we're already fine because X is dominated by V. So then we're finally in case 3. X has to be in the set capital X, the leftovers. Well, by the same argument as case 1, since I2 is a maximal independent set of X, there must be a vertex in I2 adjacent to X, and X is also dominated. So every vertex is dominated, therefore I is dominating. The next, we want to show that the size of I2 is at most D take away I1. So we're going to do this by constructing an injective function. So let's take a vertex in I2. Since D is a dominating set, there must be vertices in D that are adjacent to V. So this set must be non-empty. Let's take f of V to be some element in this set. So it's a vertex of D that's adjacent to V. Since little v was in I2, and I2 is a subset of X, we know little v is in X. Since this was our leftover set, that means in particular, V can't be in the neighborhood of any of the vertices in I1, and so that tells us this f of V actually has to be in D take away I. And thus, this function really is a function from I2 to D take away I1. So now we need to claim this function is injective. If not, there has to be two inputs that map to the same output. So we're going to call the inputs U and V. Well, then we're going to let W be their corresponding output. Notice by construction, this means that W is adjacent to U and adjacent to V. However, since I1 is a maximal independent set of D, and W is in D, there must be a vertex in I1, Z, that's adjacent to W. So now we have a claw with center W. Since G is claw-free, it follows that one of the other two pairs has to be adjacent. But U and V were in I2, so they're in an independent set, so that rules out U being adjacent to V. If U is adjacent to Z or V is adjacent to Z, then it follows that U or V are not in X, contradicting the fact they're in I2. And so we run into a problem. None of these actually work, and therefore we have a contradiction, so it must be the case that F was injective, which means that the number of elements in I2 is definitely at most D take away I1. So this allows us to get to the last claim, claim 4, that the size of I is equal to the size of D. So since D is the minimum dominating set and I is a dominating set, we already have this inequality. Meanwhile, going the other direction, the size of I is the sum of I1 plus I2. By claim 3, the size of I2 is at most D take away I1. And these two sets together form D. And so the size of I is at most the size of D, and thus they're the same size.